So, welcome to Nonlinear Optics. I'm glad that you made it in the lecture. In my other lecture, actually, so on renewable energies, we had a corona incident. And the good news is that the person who was sitting next, so immediately sitting next to the infected person, was not or is not infected. So wearing a mask, having vaccination, of course, and also, I guess, our air conditioning or air ventilation here seems to be quite efficient. I tested myself, so I'm speaking here without mask, so I tested myself just to be sure that you are safe. But I take the opportunity to make you aware of something that I learned during this weekend. I'm not sure which kind of vaccination you got. You know, there are 3 different ones that are allowed here in Germany. Namely, there is BioNTech, of course, there's Moderna, and there is Johnson & Johnson. And the advantage of Johnson & Johnson is that you need only 1 shot. And this is why a lot of people, particularly young people, preferred that. Actually, also my children did that. But it turns out that it's the least effective. And therefore, the German authorities, they actually recommend that those who are vaccinated only with Johnson & Johnson, that you get another shot, yeah, by BioNTech and Moderna. And here I have a slide. Let me, so here, no, this is not the one that I wanted to show. This one here. Yeah, so you see here the initial vaccination, say by BioNTech or by Moderna or by Johnson & Johnson. So we are now tied with chairs. So let me, so here are 2. Then maybe you try to sit somewhere. So there's one still free here. So please take this one here. And maybe we can squeeze in another chair. So here's another one that's free. We sit quite tightly packed here. I just mentioned that it's nevertheless apparently safe. Of course, I also recommend to you that you try to get a self-test from time to time. Yeah, so twice a week or so. It is free. The university has a procedure or has a station where they do this. Okay, so let me get back to a little bit of recommendations concerning COVID-19. So what you see from here is that that the antibody concentration is enhanced by a factor of more than 50 if you get a booster shot from Moderna, and also quite significantly for BioNTech Pfizer, right? So those of you who are vaccinated with Johnson & Johnson, please consider to get a booster shot. My daughter told me yesterday that she got one yesterday, and she feels quite sick today. So that's a little price to pay. The concentration of this stuff is quite high, yeah. So this is apparently the reason. So with this, let's continue with nonlinear optics, or actually with linear optics, because we said that we do a little bit of a reminder of linear optics, actually in the sense that we try to prepare for central themes of nonlinear optics. And what I've prepared are a few questions on things that we did last time. Namely, the first one is, what is the optical axis? And I hope you all installed Poll Everywhere. And now this should be active on your smartphone. Let me see whether this is the case on mine. And you are invited to, so it's active. So you are invited to answer this question. Yeah, so the first answer has arrived. Yeah. So the participation is not very large so far. So actually, it's a little bit unfortunate that that the answers are live here. So I would prefer if they only displayed a little bit later, but I don't know how to do this so far. So no more answers? Yeah, perhaps I should change this from percent to absolute numbers. Okay, so most of you answer actually. Okay, so what is the optical axis? So so the direction of light propagation in a crystal, well, that's not quite true, right? Because I can rotate the crystal as I wish. So the second option was the alignment of the crystal such that the index of refraction is independent of polarization. This is true, right? So if you align the direction of propagation in the crystal such that it's aligned with the optical axis, then the refractive index is independent of the polarization. But also this answer is correct. Yeah, for a rotationally symmetric indicatrix, for a uniaxial crystal, then the symmetry axis is also well. So why do you laugh? Yeah. Okay, yeah. Cheating. Okay, and of course the last one is also wrong. Okay, so I have the next question here, and the question is here: what is the Lorentz model good for? And you are invited to type just an answer. And then I think you can vote the different answers or something like that. Yeah? I never tried this option out. So did it update? Ah, yeah, okay. Enter response. So I guess you guys are pretty quick in typing on a smartphone. I'm not. Describe the linear frequency response of a crystal. Resonances of light, of matter to light. Harmonic approximation of electrons in light. Well, the question is, what is the Lorentz model good for? Describe the linear frequency response of a crystal. Get the n. So I think the idea is n is the refractive index, right? Get the refractive index of the crystal. Modeling the response of a charged medium. What do you mean by that? Harmonics. Okay. Well. Okay, so a lot of responses. So if you ask me, then I would. So this stopped working once again. Well, I would favor the third answer. What the Lorentz model does is that it is a model for the refractive index, right? In some sense, of course, also the first one is Yeah, now the second one is is okay, because what we did was, of course, to get a model for the for linear optics here, right? So describe the linear frequency response of a crystal. I would say this is also okay. Good. Well, it's of course a harmonic approximation of the electrons in light, in a light field. That's also clear. Well, now third. I hate this thing here. So I have to do it this way. Explain the idea of the Lorentz model with a few words. So that's the final one. And then we would continue with the lecture. Now, so what's the idea of the Lorentz model? You may remember that I explained the Lorentz model first without any math, and then we did the math. Harmonic resonance of an electron, yeah. And the electron is attached by a spring to the core and gets pushed by the electric field, so we have a damped harmonic oscillator. Yeah, assume the atoms are harmonic oscillators which are moved by the electric field of the incoming light. Electrons is a, yeah, so this pretty much describes the idea. So now let's see whether I have more luck here with this thing here. Ah, yeah. We have it here actually, so it seems to work. So we want to talk about the electro-optic effect, which is also known as the Pockels effect. And here you see Friedrich Pockels, who was a professor in Heidelberg and one of the pioneers of crystal optics. And here you see a sketch of what the Pockels effect is. So I guess the light comes in from this direction here, so we go from right to left. And this piece of material, this acts like a quarter wave plate in this case, so it produces circular polarization out of linear polarization. Right? And the interesting thing is that what one would do is, in order to induce this effect, yeah, one would apply a high voltage to this crystal. So without this high voltage, the linear polarization would just remain linear, and only by applying a strong electric field, so a high voltage, it becomes birefringent. Right? So here you see the same thing once again. So what you can do is to use this crystal and produce an electrode at the upper and lower face of this crystal, and then the polarization of this laser is changed, say from linear to circular polarization, or if you use twice the voltage, then actually also to you can rotate the polarization. Yeah? And this can also be done in this way, so that you have the electrodes at the entrance phases. Then, of course, you have to make sure that you make them transparent, these electrodes, right? So just using a piece of metal wouldn't work. Yeah, so Friedrich Pockels was an kind of important physicist, but even more important was his sister, Agnes Pockels. She had no education in physics, never studied physics, only had to do household work, and in particular take care of her sick parents, because her father actually, when they were in Venice, so he was a officer in the Austrian Empire, before the First World War, so let me connect this here. so let's come back to, yeah, so this is Agnes Pockels. So he was an officer in the army, stationed in Venice, got infected with malaria and went then to Germany and close to Braunschweig, I think. And she had to take care of them, do the household. And by washing the dishes with soap and so on, she got interested in the physics of thin films. Yeah? And made groundbreaking discoveries. Of course, nobody in Germany cared about that. So she wrote to Rayleigh, if I'm not mistaken, in England, and he took care that her report was published in Nature, right? And then in Germany, people also got interested. A few years later, so I think in 1932, there was even a Nobel Prize, not to her, but to people who had more time to investigate this. So this is Agnes Pockels. If you look on Wikipedia, yeah, so he has an article of this length or so, and her brother has an article like this. Okay, but nevertheless, it's her brother's work we are interested today. So we start with the equation for the indicatrix, right? So maybe I briefly repeat what was the origin of that, and in order to do that, let me switch to the iPad. So what we did last time was that we derived that the dielectric tensor, that this is a symmetric matrix, right? And we started to derive this by just writing down the energy density, having in mind that this is a conserved quantity, right? And so we wrote there 1/2 E times the D field. And if we write this in Cartesian components, say, right, then we get something like this, right? And now if you do the sums, yeah, so what is implicit here is actually the Einstein sum convention. Yeah, so the idea is to first sum from k equals 1 to 3, and then from j equal to 1 to 3, right? So perhaps I write this explicitly. So this is 1/2, and then by definition, yeah, j from 1 to 3 and k from 1 to 3 ej epsilon jk dk. Yeah? But this is not the point here. The point is that we wrote it down so that we derived that it's a symmetric tensor, and then this here has the form of epsilon 1 E1 squared plus epsilon 2 E2 squared plus epsilon 3 E3 squared. And then the mixed terms, but with a factor of 2 because it's a symmetric tensor. So we have 2 times epsilon 3 E2 E3 plus 2 times epsilon 3 E1 E3, and then the final one 2 times epsilon 2 E1 E2. Right? So what is the...
The first one instead of E, it should be E.
Because D is equal to E epsilon jk multiplied EK, right?
Yeah. Sure. Sorry, yeah, thank you. Yeah. This makes, of course, no sense. Yeah, thank you. Okay, yeah, and of course, the second line here proves you also right. And this, so this is basically the equation that with which I started here on this slide here, right? So if you divide or if you normalize it to the energy density, then you arrive at this equation, right? We are not in the principal axis system, yeah, so Hauptachsensystem. But anyway, yeah. So far, everything is field-free. Now we apply a field, and this means that the dielectric tensor is changed. So think about the following. You have a tensor, so you have a kind of a matrix, and now you apply a field, and this changes this matrix. What do you need in order to describe this mathematically? What you need is another tensor, and actually a third-rank tensor, in order to describe the changes to this original tensor. Yeah, so we have here the tensor Bij, and now we change it due to this external electric field. And in order to describe this in a linear approximation, you need this third-rank tensor. Yeah, so I call it R. And it has, in general, 27 components. Yeah? But we know already that this one here is symmetric. Therefore, this doesn't have actually 27 components, but instead just 18. Yeah? So 18. This sounds pretty terrible, right? So it sounds a little bit better than 27, but actually 18 or 27, yeah? So if you're confronted with that, that doesn't make much difference. Well, the fortunate message is that for most crystals, actually, it's not 18 components. It's due to symmetry reasons, and we'll come to that, it's just a few components. Yeah? Sometimes even 0 components. Yeah? So sometimes this thing here vanishes altogether. Okay, for example, if you have a crystal with inversion symmetry, then inversion symmetry means that the crystal is transformed into itself by inversion, yeah, so by taking the negative of all indices, and then you find that the electro-optical effect vanishes. We'll come to that in a little bit more detail later again, just as a first example that that things are not quite as bad as they might look on first glance. So now we do a trick, and it's actually a trick that has nothing to do with physics. It hardly has to do with mathematics. It's a really cheap trick to make to avoid dealing with a third-rank tensor. Yeah, so we can write matrices very conveniently because we have two-dimensional papers, right? Unfortunately, we don't have three-dimensional papers. If so, we wouldn't use that trick. Yeah? And what we do is that we produce out of this matrix B, we convert it into a vector. Yeah? And this tensor R, we will convert into a matrix. Right? So we have 6 components because we said that this tensor here is symmetric. And so what we do is that we say the index combination 1, 1 we convert to 1, to 2, to 2, and 3, 3 to 3. Right? The question is, what do we do with 2, 3? Yeah, we convert it to 4, 3, 1 to 5, 1, 2 to 6. Do we have a chance to memorize that? Well, in Germany we say one needs an Eselsbrücke, a donkey's bridge, right? And here it is. So if you sum them up, 2 plus 3 plus 4, then you get 9. If you sum 3 plus 1 plus 5, you also get 9. And then if you have this here, you get also 9. Yeah, so just memorize that the sum of these indices is equal to 9. So this means that we convert this matrix, which is actually symmetric. Yeah, so these two here are equal, as well as these two are equal, and these two. Yeah, then we convert this to this vector. And also it changes to this vector delta B. And now we can do the same thing here, of course, with these matrices. Right? With this tensor here, we convert it into a matrix. So we have a matrix that has 3 columns and 6 rows. Good. Yeah? Just a trick. Yeah? Well, let's come back to physics. So the applied field changes the refractive index. Yeah? So, which means that the modified kind of 3-dimensional refractive index, they can again be described by an indicatrix. Yeah, so you remember this ellipsoid representation of the indicatrix. So now suppose that the original indicatrix, so the indicatrix without an applied electric field, is in the principal axis system. Then this means that the off-diagonal elements are equal to 0. This is how the principal axis system is defined. Right? Now we apply a field, and then the off-diagonal elements of this matrix, they are no longer equal to 0. Right? So the new indicatrix is in this coordinate system that we have up here, yeah, is not in the principal axis system. Yeah, so when we were initially in the principal axis system and now apply an electric field, then we are no longer in the principal axis system in general. Yeah? But what we can definitely do is to rotate our coordinate system such that we are again in the principal axis system. Right? And this is pretty much what we are going to do. Right? So here I described without mass what we are going to do. Good. Yeah. So what we will do is that we will confine ourselves just to an example, to a rather simple example. So we use a certain crystal ADP, ammonium dihydrogen phosphate. I'm not a chemist. I have no idea what it is in particular. It's a useful crystal in optics. Yeah? So that's good enough for us. It belongs to the crystal class 4 bar. Right? So it has a 4-fold inversion axis. Yeah, and perpendicular to that, a 2-fold axis, yeah, so rotational symmetry for rotation about 180 degrees and a mirror plane. So it's a uniaxial crystal. Yeah? Without an applied electric field, it's a uniaxial crystal, just to make this clear. Right? And you can already guess, if I apply an electric field, it's no longer uniaxial, but has two optical axes. Yeah? So now we select the coordinate system that without the applied electric field, we are in the principal axis system. And we define this variable O, reminiscent of the ordinary index of refraction, as 1 over NO, and the same for the extraordinary index of refraction. And then the indicatrix reads like this here, right? Okay. So now a next preview. So this subchapter is actually full of previews to nonlinear optics. So I introduced this trick with this, it's called contracted notation. So this thing where one converts a matrix into a vector and a tensor into a matrix. This we will also do in nonlinear optics, right? And also this, what I show here, namely that this tensor, third rank tensor, which is now just a matrix, that this has just a few components due to all these symmetries here. We'll also come to that in a later chapter. It turns actually out, if you apply all these symmetry operations, so the idea basically is, if I have, say, the symmetry operation of this mirror plane and apply it to the tensor, then the tensor must be identical to the tensor without application of the symmetry operation, right? Because what means symmetry? Symmetry means that if I, say, apply this mirror plane, that the lattice of this crystal looks exactly like without applying this mirror plane, right? And if the crystal looks exactly before and after application of the symmetry operation, then all its physical properties need to remain the same, right? So this is the idea, right? And this creates, of course, a lot of equations that must be fulfilled. And in this case, it turns out that the only non-zero elements are these here. Yeah, so R41, well, would you be able to tell me immediately what 41 stands for, actually? Yeah, 9 minus 4 is 5. And what do I need to combine from numbers of 1 to 3 in order to get 5? Yeah, 2 plus 3. So what this here is 2, 3, 1. Right? And so only 3 components that are non-zero, and even 2 of them are equal. Yeah? So 18 components look terrible. Now we have just 2. Well, even this is too cumbersome for us. Yeah? So we want to take it easy today. And therefore, I decided to assume that we have an electric field where we have only the third component. Yeah? So in the principal axis system, I would call this Ez. Right? And then this change to this B vector or tensor, yeah, this has actually just a single component. Right? Okay, so this is the change to our original equation that follows from the application of an external, in this case, static electric field. Now, if you compare what has changed, yeah, so we had this situation in the principal axis system. In the general form is this one here, right? And what you see is that, well, these terms here, they are, they don't play a role if you multiply this out. And the only new term we get is this one here, right? And we have an expression now for it. Yeah, so assuming that this third rank tensor R is known, we now know exactly what is done to the indicatrix by the external electric field. Good. So I announced what we are going to do. Yeah, so what we see here is that we are no longer in the principal axis system. So what I said is that we will rotate our coordinate system such that we are again in the principal axis system, and yeah, we need to rotate the coordinate system. Yeah? And what you see here is that this thing here doesn't depend on z, right? So just on x and y. So it's immediately clear that I need a rotation around the z-axis. Yeah? And a rotation around the z-axis is, well, maybe a rotation around alpha, and then I get the following coordinate transformation. Right? You can read this immediately. You can immediately read off this here. And the next step is also immediately obvious. We would substitute this into this equation, right? So we need to calculate this here, which is pretty simple, right? So you need the square of that binomial formula, right? And you see here we have a minus sign, so this mixed term in both, yeah, so if we add x squared and y squared, then the mixed term cancels. And then at the end we have actually x prime squared cosine squared plus x prime squared sine squared, right? So we would factor out x prime, and then we have sine squared plus cosine squared, which gives 1. Therefore, this here is simply the same thing, right? So in the primed and unprimed coordinate system, this doesn't change. Well, you could have guessed this immediately. Yeah? For the third term, there's of course no change because we rotate around the z-axis, and so we need to calculate the last term, right? So xy. Yeah? So we want to calculate xy here, and we just substitute these two things here in here, yeah? And then we multiply it out stupidly, and then we find that there's the product of sine alpha and cosine alpha. I'm not sure whether you remember the trigonometric identities. Who knows them all? Nobody? I also don't know them. I have to look them up usually. Well, this one I probably use often enough to know it. So in any case, this is 1/2 sine 2 alpha. I encircled this just in order not to forget this factor down here, right? And this here is cosine 2 alpha. Yeah? Okay, so now it's good to remember what we are after. Yeah? So in a calculation, it's often the case that you lose track of what you want, right? What do we want? We want to have this, to get rid of this term here, right? So we want to make this here 0, right? And of course, if you now rotate it by alpha equal to 45 degrees, then 2 alpha is of course 90 degrees. Then the cosine of 2 alpha is equal to 0. Right? So this kills this term here. Yeah, so then this factor here is equal to 0. And the other one equal to 1. Yeah, and then this equation reads like this here. Right? And now we can resort it. Yeah, so we can collect the x prime squares. Here's another one. And the y prime squared squares. Yeah? And then we arrive at this situation here. Yeah? And now you see we have x prime squared, y prime squared, z prime squared, and no mixed term. So we are in the Hauptachsensystem. in the principal axis system. But what you realize is that this term here now, so the prefactor of x prime squared, is different from the term, from the prefactor of y prime squared. In other words, we now have a biaxial crystal. Yeah? Just as expected. It's always good to think about what you are going to do in a calculation. Right? Actually, there was a famous physicist, I think it was Wheeler, who said, you should never start a calculation without knowing the result, at least qualitatively. And this is actually what we did. Right? So we got what we expected. That's reassuring. Good. Yeah, so the crystal becomes biaxial. This is the remark here. Oh, there's here an interesting thing, right? So if you look at, maybe I go back to here, right? So what you see is that this alpha is just 45 degrees. And the angle by which we need to rotate this crystal in order to get it back to the principal axis system is 45 degrees. No matter how strong the field is. Wouldn't you have expected that if I have just a tiny electric external field, that I need to rotate it a little bit? And if I apply a stronger electric field, I need to rotate a little bit more? For me, this would make sense. So what about you? Yeah? Alpha is independent of the applied field. Can this be true? Yeah, so I just was talking about contemplating of what the result would be. Right? So in part we got it, but in the other part there was a surprise. Right? Can this be true? Yeah, so there are some of you say no, some of you say yes. Yeah, so if you answer yes, then this is of course dangerous, because you can imagine what the next slide will be here. Namely, that I ask why. Right? Okay, so the next question is why. Not everybody takes part in our little games. So no answers so far. Yeah, so all those who answered yes, they did it just because you trust me, right? So I appreciate that, of course. Oh, what's up here? No idea? Ah, yeah. It depends on the crystal. This is kind of true, actually. It depends on the crystal. Okay, so let's solve the puzzle. Let's reveal the puzzle. So here again the problem, right? So actually the point is we are looking in z direction and we have a uniaxial crystal. Yeah? So we have actually so we are looking in direction of the optical axis, right? And we could have started out with a different principal axis system, right? So if you have a uniaxial crystal, then of course you can rotate your original coordinate system by any angle, and you are still in the in the principal axis system as long as you rotate just around the optical axis. Isn't this true? Does this make sense? Right? So it's rotational symmetric, the indicatrix, and therefore I started just, well, kind of with the wrong principal axis system, with the wrong coordinate system. Well, it's actually not wrong, yeah, because it makes some sense to use this, because the original one was just aligned to the axis of the unit cell. But anyway, right? So I think you got the idea. So now, if we compare now this equation 77 with equation 60, well, I have it here for your convenience, right? So if you compare these two equations, then we can identify who is who, right? And we would find that nx is equal to 1 over square root of O squared minus R63 times Ez, and the same for B2, but with the only difference being this sign here. What we do next is about power series expansion. Yeah, so we take a Taylor expansion here, and we arrive at these two expressions, yeah, so quite straightforwardly. And then we find for nx this expression here, and for ny we find this expression. Right? And now you see very intuitively that if you have a beam that propagates in z direction in this coordinate system, that the two polarizations in x and in y direction, they feel a different refractive index depending on, this is probably a capital Ez, right? Yeah, this is certainly capital Ez. So depending on the electric field, you see a difference in the refractive index for these two polarizations, right? And therefore, if you shine in your laser or whatever light at 45 degrees with respect to the x and the y axis, then you can decompose, of course, the field vector in x direction and in y direction, and they will be phase shifted with respect to each other depending on the electric field, which unfortunately here is written with small ez. Right? The larger you make this, the bigger the difference in the index of refraction. Well, and now we can calculate the optical path length, of course, according to that. Yeah, so we assume a certain length of the crystal, yeah, say capital L, and then the optical path length difference is given by this thing here. Right? And now we can ask ourselves, which kind of electric field do we need to apply in order to make the optical path length difference, say, lambda over 4? Because what happens then if it is lambda over 4, the optical path length difference? Yeah, then we get circular polarization. Okay, yeah. So, and now we can say, which is the electric field in order to make this crystal to a quarter wave plate, so to say, right? And, well, how to create an electric field? Of course, we have to apply a voltage, right? And a voltage, so the electric field due to a voltage is, of course, voltage divided by distance. And what's the distance? This is, of course, the length of the crystal. And you see that this L cancels out here, right? So this is this, this would be here, the thickness of this crystal in this case would be this L, right? And therefore, we can speak actually of, say, the the quarter wave voltage or the half wave voltage, right? So what we need here, we find that the optical path length depends on the voltage. So here you see what I just mentioned. Okay, by applying a certain voltage, you can rotate the polarization by 90 degrees. This is the half wave voltage. And this immediately suggests how to use this effect. Namely, you can build an electro-optic shutter. You can build a very fast shutter by just putting a polarizer behind the crystal, right? That then would block either the light with a polarization without the voltage or with the voltage. And one can apply voltages quite fast. So you just need a fast high voltage switch. And then you can switch on and off light with nanosecond resolution or so. So what do you think actually when this was done for the first time? 10 years ago, 20 years ago, 50 years ago, 100 years ago? 1960s, 70s, so with high voltage electron tubes? Certainly. Right?
Not sure now. But then
Yeah, so probably not yet with a transistor, but certainly with an electron tube. Could it be earlier? If I ask this way, then probably yes, right? Could it be earlier? It can, yeah. So you would just take a spark gap. Yeah, so this was high tech at the end of the 19th century. Yeah, so in the beginning of the 20th century, they could build electro-optic switches with, if necessary, nanosecond time resolution, right? To take, say, a photo of a flying bullet or something like that, right? Would be perhaps one application. Okay, anyway. I think this is the end. Oh, yeah, so this is already the next one here. This is for the next chapter already. So what I want to write down for this chapter 1, you know, I just showed it on by PowerPoint because it's kind of, yeah, not part of the curriculum because it's linear optic. But nevertheless, I would like to write down a few take-home messages. Yeah, so take-home. So I should switch to this one here. Take-home messages. Yep. The first point here was that we discussed the significance of nonlinear optics. Yeah, so why nonlinear optics is important, and actually there are so many reasons that that it's impossible to give a complete list of that. All right. One of the interesting points was that with nonlinear optics, it's possible to create new colors. Yeah, so you have never seen green light going through a window, and then after the window you have another color suddenly. Or red light going through a crystal, and out comes blue light. In nonlinear optics, this takes place. Yeah? So the significance of nonlinear optics yeah? And the other point that's equally important, yeah? Not only creating new colors, the other point is that the intensity of the new color depends in a nonlinear way on the incident intensity. Yeah? And this has actually many, many applications, for example, in spectroscopy. Yeah, so all the breathtaking advances in spectroscopy, laser spectroscopy in particular, of course, would not be possible without nonlinear optics. So, significance of nonlinear optics. So, what it is, yeah, so nonlinear optics, this means that the refractive index becomes intensity dependent, or the polarization, which in linear optics is written like this, needs to be, well, we need to add some terms, yeah, which are non-zero. We were talking about the Lorentz model, yeah, and we'll come back to the Lorentz model. We treated it as we treated the material as a harmonic oscillator, and we will just expand our model a little bit, and then we have a nonlinear oscillator. Of course, a nonlinear oscillator is much harder to deal with than a linear oscillator, but this is the other thing I said, namely that the mass of nonlinear optics can be quite ugly, and usually is quite ugly, I have to admit. So we introduced this this tensor here, and we will have to deal with a lot of other tensors also. What we found is that this here is symmetric. Yeah, so it is symmetric. Then we were talking about birefringence. And birefringence, we will learn, is quite important for an effect that's called phase matching. Yeah? So the problem in nonlinear optics is that material has dispersion. Right? So say you want to do frequency doubling, which means that you come in with red light and you get out blue light. Then you know that due to dispersion, the refractive index for the blue light is larger than the one for the red light. Yeah? And therefore, the blue and the red light, they get out of phase. And this is, of course, a problem, because then in different pieces of the crystal, you create blue light that is not in phase with the blue light created earlier in the crystal. Right? And therefore, they start to interfere destructively. This is not what you want. Right? So this is one of the challenges in nonlinear optics. And birefringence is an important ingredient to solve it. Yeah? Because then you suddenly have in a crystal two refractive indices, and you can start to play with it. Yeah? So birefringence plays a big role in nonlinear optics. So, and then we had the electro-optic effect. And, well, the next chapter is a preview to nonlinear, it's a survey of nonlinear optics effects. And in some sense, the electro-optic was a preview of nonlinear optics. Yeah? So the electro-optic effect, in many respects actually, as a preview to nonlinear optics. So these are the take-home messages for the first chapter, which means that we are done with the first chapter and we advance to the next chapter. Namely, as I said already, it's a survey of nonlinear effects. So chapter 2. And this is kind of an important chapter. as most chapters that follow. And it's of course new, and therefore I will write a lot of things here on my iPad, and such that you have time to also write down notes. So, survey of nonlinear effects. So, and we start with a brief introduction. So, to an introduction, and for the introduction, right away my next question that I prepared for you, namely this one here. How would you generalize the linear relation of the polarization and the electric field? Yeah? So think about it. Yeah, so what we had is what we had was that we had P of t is equal to epsilon 0 times chi times the electric field. Yes, this is what we wrote down so far. How would you generalize that? Yeah, unfortunately, there's no LaTeX on Poll Everywhere. Well, actually there is, but it doesn't work properly. As a usual, Taylor series. This is one answer. D. No more answers. As a usual, Taylor series. Include higher order terms of E. Yeah. Okay, let's try that. Yeah. So we generalize. This one here by doing what you said, by adding higher order terms, right? And because we are not, we don't have fantasy enough in order to use here other susceptibilities, we say that the first one, yeah, so that the usual one, the familiar one, we call chi 1, and the next one we call chi 2. And then we would write down here the square of the electric field, and then if this is not enough, then we would write down the cube of the electric field together with a susceptibility of third order. Right? And then you could add more and more terms. And there are colleagues who go up to 30 terms or something like that. I don't think that this makes sense. Because after all, well, a Taylor series expansion has little to do with physics. Well, actually a little bit. So there's a qualitative difference between chi 2 and chi 3 effects. So this is of significance. But then chi 4, and chi 100 or something like that, this does not really make sense, in my opinion. And we can write this now as first order, second order, and so on polarization. Right, so something like this here. Well, perhaps I should write it here just to make clear who is who. But I think this is clear anyway. Yeah, so we have first order polarization, we have second order polarization, and so on. Okay. So chi 2 and chi 3 are known as second and third order nonlinear optical susceptibilities. Yeah. Chi1 is a second rank tensor. Yeah, looks like a matrix. Second rank tensor. Then, of course, Chi2 is a third rank tensor. And Chi3 would be a fourth rank tensor. Yeah, a lot of components. In general, all independent components. But anyway, so what I have to say here, this equation 1, this is actually already a simplification. Does anybody know why this is a simplification? What's wrong with this equation? Yeah. Sorry, what did you say? Okay, you know already a lot of things, yeah? So what we assume here is an instantaneous response. Yeah? So what we say is that the polarization at this moment is only influenced by the electric field at the same moment. But it could well be that the polarization today is actually due to something that happened yesterday. Right? That would be fair enough. Well, what's of course not possible is that the polarization today depends on what happens tomorrow. Right? We call this causality. But actually, what we would have to do in order to make this here correct would be to add up all the contributions of what happened in the past. Yeah? This we didn't do so far. But at some point, we'll do that. Yeah? Sorry, I didn't understand.
In non-linear, the phases are very important.
Yes?
If we assume that the response is instantaneous, then the model is accurate enough to discard the material non-linear crystals.
Well, depends on the situation. Right? So there are definitely materials that respond very quickly and have no memory, right? Respond very quickly and have no memory. For those, this approximation is a very good one. And actually, most of the effects that we are concerned with for this approximation is actually quite good. Yep. Okay. Well. So let's write that down. So equation 1 is only valid for media whose polarization depends instantaneously on field strength. Yeah, on field strength E. Yeah. And these are idealized media. They are lossless, and they exhibit no dispersion. Right? Yeah. Such idealized media are lossless and have no dispersion. Yeah, so this sounds like two properties, but actually it's just one property. Media that have no dispersion are lossless. And lossless media don't have dispersion. Do you know this property or this connection? No? Yeah?
What do you mean by lossless?
So that if you shine in light, that as much light comes out as goes in. This is lossless. Yeah? No absorption. Yeah? So for material which have absolutely no absorption, they also don't have dispersion. Did you know that? No? This is Kramers-Kronig relations, right? And Kramers-Kronig relations also part of linear optics. But this is a very interesting relation because you just make a few very simple assumptions, namely that you have causality, yeah, which in physics we tend to believe, right? Causality. Then what else do we have? We have a linear, something linear, and there's a third thing that I forgot now. Yeah? And with these basic assumptions, you arrive at such a profound conclusion. Yeah? So you should, so if you haven't heard a course in optics with this, explaining this property, the Kramers-Kronig relation, you definitely should learn this material. But it's not part of linear, nonlinear optics, so I don't do it here. Okay, well, we have to define what P2 and so on is. P2 is referred to as second order polarization. And of course, the same thing here, just with third order polarization. Now, the next point would be that we look at the order of magnitude of these susceptibilities. Right? So if you look at this first order susceptibility for some material, what's the order of magnitude? How big is it? Actually, what's the unit of this thing here? That could have also been a nice question for Paul everywhere. What's the unit of the susceptibility? In SI units, of course. Oh, second semester, huh? No? The unit is 1. Yeah, so the unit is, of course, E and P, they have different units. Yeah, so this is volt per meter. This here is the dipole moment per, so charge times distance divided by volume, right? So this here needs to convert between these units. And this has, well, no unit, unit 1. Yeah. And actually, what's the magnitude? What's the magnitude of the susceptibility? So the order, well, of course, different materials have different susceptibilities, but for some solid piece of glass, so what's the order of magnitude of this thing here? I guess you should know that. It's 1, right? Because the refractive index of some piece of glass is perhaps 1.5, right? And you know that that there's a relationship. So we had this in the first lecture. There's a relationship between the susceptibility and the dielectric constant, the relative dielectric constant, which has a direct connection to the refractive index. Right? So the square root of the dielectric constant is equal to the refractive index, and the susceptibility is 1 plus the susceptibility, right? So you remember that. Okay, so this is the order of magnitude of the linear susceptibility, right? Has magnitude on the order of 1 and no unit, right? So to find the unit now of chi 2, this is of course simple, because it needs to be meters per volt, because we have now the square here, and here we have it just linear. Right? So this must be meters per volt, but how big is it? Yeah, so this is what we want to find out. So the order of magnitude. Order of magnitude of chi 2 and chi 3. So, and what we do is a little bit hand waving. I have to say, I have to admit. Namely, what we say is that that at some point this Taylor expansion will break down, right? So this Taylor expansion will break down as soon as the higher order terms become as big as the lower order terms. Right? Then this entire power series expansion doesn't make any sense any longer. Right? And now we can try to guess at which field strength this happens. Right? And the idea is to say, well, once the field strength of the laser is as strong as the field strength that holds the electrons in place, yeah, then this is certainly going to break down. Right? And so we say, well, if we think about the most naive model of some piece of optical material, then we could think of the atoms as just hydrogen atoms, right? And the electron is in the ground state on the first Bohrian radius, and there's a certain field strength there, which is actually known as the atomic field strength. Right? And if the laser has a field strength that is as strong as, well, the field strength of the proton on the first Bohrian radius, what is the distance actually of the radius of the first Bohrian orbit? Do you know? 0.5 angstrom, right? So approximately 1 angstrom, because this is the size. So an angstrom is 10 to the minus 10 meters. Yeah? A tenth of a nanometer. So if you calculate that field strength, then you arrive at a value of 10 to the 11 volts per meter. 10 to the 11 volts per meter, right? And this corresponds to a certain intensity. Yeah? So you can calculate the intensity that corresponds to that field strength. These are 3.5 times 10 to the 16 watts per square centimeter. Yeah, so a huge field strength. But at this field strength, we certainly expect that this thing here breaks down, right? And if this, yeah, so at this field strength, we can assume, or we can guess, that all these terms here are of equal magnitude, right? So all these terms are of equal magnitude. Yeah? Okay, let's write that down. So we assume that at the atomic field strength, at the atomic field strength, Yeah, so this is an electric field equal to the field of a proton at the first Borean radius. Yeah, so we assume that at the atomic field strength, all terms of equation 1 are approximately equal. Yeah. Yeah, and this would then mean that chi 2 is approximately equal to chi 1 divided by the atomic field strength. Yeah? And similarly, chi 3 is equal to chi 1, which is approximately 1, by the way, as we discussed, divided by the atomic field strength squared. Yeah? So the atomic field strength, let's write that down, the atomic field strength this is equal to 3.51 times 10 to the 16 watts per square centimeter. Right? And using this, we immediately find the order of magnitude of chi 2 and chi 3. Yeah? So for condensed matter, like a piece of glass, we have chi 1 is approximately 1, and this means that chi 2 is approximately, well, 10 to the minus 12 meters per volt, and chi 3 10 to the minus 24 meters squared per volt squared. Yeah. Well, one remark to finish this introductory subchapter. I said that at the atomic field strength, the laser field strength is equal to the field strength of the proton on the first Borean radius, which implies that such an atom will be completely ionized, will be immediately ionized by the laser, right? And if you ionize all atoms in some material, then of course this means that the material is destroyed. And actually it will be destroyed long before you reach the atomic field strength. Yeah, so it's not possible to expose condensed matter to the atomic field strength. At least not with optical lasers. So how much time do we have? Not much. Not much. But nevertheless, I start with the next point, and actually I think we will be quick enough to learn at least a little bit. Namely, I want to discuss second order. No, actually second harmonic generation. I will start with second harmonic generation, which is arguably the most important effect of nonlinear optics anyway. Yeah, and it's abbreviated with SHG, second harmonic generation. Second harmonic generation. Yeah, and we do what we just kind of said, namely, we have a laser. We just write down the laser, the electric field of the laser. Yeah, so we have a laser with electric field strength. It's just an oscillating electric field. So we have E of t equals the amplitude times e to the minus I omega t. This is complex, right? And in order to make it real, once again, yeah, so the electric field is a physical quantity, therefore it is a real number plus a unit. So and now this here is complex. Actually, also the amplitude is assumed to be complex in order to allow phases. And in order to correct what we just made wrong by writing it complex, we add the complex conjugated. Yeah. So now this laser with this electric field strength is incident on a crystal where the second order dispersion is non-zero. Yeah, on a crystal with non-vanishing chi2. Yeah, it's worthwhile that chi2 can vanish. Actually, it does so for most materials. So then, according to equation 1, the second order polarization is given by, so we have now P2 of t is epsilon 0 times chi 2 times E of t, right? Squared, of course. Right? And now we write this explicitly. So we substitute here this equation 5. So epsilon 0 times chi 2 times, and now E times e to the minus I omega t plus E star, complex conjugated, E plus I omega t. And the entire thing squared. Right? Okay, what do we get? Of course, we get binomial formula, very simple. We could have done this in high school. E squared times e to the minus 2I omega t. Right? Plus, now the mixed term, 2 times E star. Right? So the interesting point here is that e to the minus I omega t and e to the plus I omega t, that they cancel each other or multiply up to 1. Right? And now the last term, E star squared, and then we have e to the plus 2I omega t. Right? Okay, we reorder the entire thing a little bit. So the middle term here, 2 times epsilon 0 times chi 2 times E star. Right? And then we have the other two terms. And you see actually that the second term is just the complex conjugate of the first term. Right? So we have epsilon 0 times chi 2 times E squared times e to the minus 2I omega t plus its complex conjugate. So what you see is that actually this term here is a real number, right, is a real quantity because here we have the complex conjugate. And this term is also a real quantity, right? Because we also have here this complex number here and the complex conjugate of this thing. So both are real things, right? So we would expect that both terms, that they have some correspondence in the real world, right? So that we find an effect that is that corresponds to these terms. Well, the second one is the easy one, right? What does the second one describe? Stupid question. The second one oscillates with the frequency twice the original frequency. So that's second harmonic generation, as the headline indicates, right? The interesting part is the first one here, right? What does this correspond to? It's a DC polarization, right? So it's a DC polarization. So it has no frequency dependence. Yeah? So this is, so you come in with an oscillating field and you get out something, you come in with an oscillating electric field and you get out an electric field that is not dependent on the frequency. It's a DC field. So this is rectification. This is optical rectification. Yeah, so it's quite interesting that we did almost nothing here. We did really stupid elementary stuff and we got out a surprise. We got out more than we expected. We certainly expected frequency doubling, right? And the headline indicates it. But that we got for free also optical rectification is kind of interesting, right? Next lecture we'll come also to third order processes. And again, we'll see that we'll get more than we have ordered. Yeah? Okay, let's write down this here as a final remark. Yeah, so this here is optical rectification. Yeah, a DC field, while this here is second harmonic generation. Okay, so we did a little bit of nonlinear optics already, and with this I close for today and wish you a good week. See you next Monday. This one.